It's a blessing to be here.
Today we have Kirk Sorensen.
I'm very excited to be here at Google.
Thorium is an element. It is slightly radioactive. It is a metal. It's got a very wide liquid range, some other interesting properties. Thorium is not really commercially used for anything of much these days. This is a log scale of what's available in the Earth's crust, and you see that at the beginning you have oxygen, silicon, aluminum, and towards the bottom you got lead and thorium. The uranium that you're really interested, the one fissile material, is orders of magnitude less.
Thorium itself is not a fissionable fuel. How can it be a fuel?
Three kinds of radioactivity. There's alpha emission, there's beta emission, and there's gamma emission. But the basic idea is there's 4 natural decay chains because an alpha particle has a mass of 4. And so every time you drop an alpha, you change by 4. Now one of them's extinct, neptunium here, but the other 3 we find in nature. And they're the source of all of our naturally radioactive materials. Once you figure out how matter really works, you realize that nuclear fission is an incredibly dense source of energy. Nature gave us 3 options for fuel. The one on the top is what we use all the time. And now paint yourself in the late 1930s, early 1940s. This is when they figured out that uranium-235 could fission. Glenn Seaborg told his students, hey, go figure out if we can make something fissile out of uranium-238, which is much more common. They could make plutonium. And then Seaborg began to figure out that, hey, you know what, I'll bet if this worked on uranium-238, I'll bet it would work on thorium too. And sure enough, all 3 of these could be made to make nuclear energy. So what's the distinction between them? Well, it's a wartime scenario. So the first question was, how do we turn it into a weapon? This to me is one of the great tragedies of nuclear energy. It was discovered in context of a war.
What did we do? We went from weapons to the Nautilus, Eisenhower's Atoms for Peace program, or let's produce electricity. But you're using the same infrastructure, the same people, the same needs and desires. You pour it into here. Sure enough, that is the base product for our surface ships. A little bit of entangled there. It wasn't exactly Atoms for Peace in a conventional sense of what's the best way to produce electricity.
All of these were initially evaluated in terms of their destructive potential. Natural uranium, isolate that U-235 and they could make a bomb out of it, and that was Hiroshima. Take the remaining uranium, irradiate it, and you could make plutonium and you could make a bomb out of it. Now what about thorium? Could you irradiate that and make a bomb out of it? It's a really bad idea. It's inevitably contaminated with uranium-232. Uranium-232 is decaying and throwing off gammas and basically screwing up your weapon. Trashing your explosives, it's trashing your electronics, and it's telling everybody where it is. So thorium's no good for nuclear weapons.
You can take a little bit of thorium, put it in a normal reactor, and you get some benefits out of it. But it's not an end-all. It doesn't extract all the energy out of that thorium that you'd like to. And it doesn't mitigate all the problems you have with today's nuclear power.
Here's what happens in today's light water reactor. You start off with about 250 tons of uranium. Some of it's enriched. About as many fission products come out as products go in, makes sense. Most of the stuff that comes out is U-238, it's not burned up, but there's about a ton of fission products and about 0.3 tons of plutonium that come out of a typical gigawatt plant. A thorium reactor, it only uses a ton of thorium because we burn all of it. And out of this thing, we get about 0.0001 ton. We get about 100 grams of plutonium. There's 2 reasons for this. Thorium-232 has a much lower atomic mass than does uranium-238. And in order to make plutonium, you need many, many more neutron absorptions successively. So the probability of making plutonium in that kind of reactor is much, much less. The second reason is that the plutonium stay in the fuel salt and in turn eventually fission, absorb a neutron, or otherwise consumed.
Uranium and thorium together, they both have the same energy density if you fission them all up. The real advantage is the ability to fission up the thorium all the way in a thermal reactor.
In the case of a nuclear energy, what if you could take some of the cons out of there, safety fears and long-term sustainability, proliferation issues, and make them go away or minimize them? Sounds like what fusion wants. There were a couple of Google talks making fusion in a way that's smaller. I would love that to happen. But basically, we've got these very large plants, and they produce a lot of energy, but they also absorb a lot of energy in producing the energy. Net gain, not as good as you would want.
We've all seen this picture before, the chain reaction. The natural inclination when you look at the picture is, wow, this is bad. This is getting away on us. This is not controllable. I don't like this thing. But then I went to nuclear engineering school, and they taught me about what criticality is. And this is another word that's kind of entered our vocabulary in a negative way. It's going to go critical. Like, that's a really bad thing. Well, it turns out criticality is just a state of balance. If you have 10,000 fissions and you get 10,000 more fissions, that's critical. your reactor is going to stay at the same fission rate. If 10,000 fissions lead to less, then it's subcritical. If they lead to more, it's supercritical. But I mean, these can be controlled. And how can they be controlled? If we construct a system that feeds back on itself and has a response, then it will naturally dial itself into criticality. And the analogy I use is a mass on a spring. If you try to put the mass at just the right location where the spring balances the force of the mass being pulled down, it's pretty hard to just know exactly where that point is. But you let it go, and what happens is the spring will gradually take you into the right place. The same with a reactor. You want your reactor to naturally control itself. We can build self-controlling reactors. Reactors are not necessarily twitchy. You can build bad reactors that have unpleasant characteristics, but you can build good reactors too.
Enrico Fermi argued for the plutonium-based economy, and one of the reasons is you get 3 neutrons on average per fission, and you need at least 2. You need 1 to split and 1 to breed your next fuel. You're using the fast neutrons coming off the reactor from the fissions. And you can see that this number really climbs very good, which means you get a whole lot more than 2, which means you get production of plutonium.
For that reason, all the emphasis was turned towards the uranium-plutonium cycle because of the necessity of making nuclear weapons.
Wigner said, no, that's not such a good idea. Thermal fission is the way to go. We want to use slowed down neutrons. By doing that, we're going to have safer reactors. We're going to have easier to control reactors. We're going to be able to employ those mechanisms that I was talking about that control natural criticality. And the only way to do this was to use thorium. This was kind of a fork in the road back during the Manhattan Project. One guy went off one direction to go work uranium-plutonium. The other guy went the other direction to work thorium and uranium-233. And the reason a thermal reactor is so different from a fast reactor is this is what these nuclei look like to neutrons. I mean, if you were a neutron in a reactor, you would see up here on the top row, that's the thermal spectrum. Big targets. And the blue represents if you hit it, you're going to cause a fission, and the red represents if you hit it, it's just going to absorb. It's just going to eat the neutron. Look, plutonium's a big target. Well, a third of the time you hit it, you're just going to get eaten rather than cause a fission. Uranium-233, most of the time you hit it, you're going to cause fission rather than an absorption. Now look down here at the fast spectrum. You can't see it at this scale, but most of the time you hit the nuclei, you're going to have a fission. The problem is you don't hit it very often. So a thermal reactor gets a lot better fuel efficiency. You need a lot less fuel to get the same amount of heat. The upshot of that is a thermal reactor like Lifter can get about 5 times more heat per unit fissile fuel than a fast reactor can.
Look at the uranium cycle compared to the thorium cycle. You start out with a whole lot more mining with the uranium cycle. You have a whole lot of yellow cake that you make, but then you got to enrich that and then make these pellets. It's a very expensive process. You end up with a whole bunch of depleted uranium. It's still useful in some ways and not useful in others, so I don't know what people are doing with that other than letting it sit on the ground. It doesn't go to Yucca Mountain. You need a very big plant with a vessel that can hold up all the steam or any explosion that can happen here because it's very high pressure. Big turbine plant next to it, and you produce a whole lot of spent fuel, and you need Yucca Mountain for 10,000 years. The thorium cycle, you need 1 ton. This is for the same amount of energy, 1 gigawatt for 1 year. Much smaller plant, low pressure. Braytons are much smaller, much more efficient, as much as 50% efficient or better compared to about 35% best you can do for steam. But the big deal here is that in 10 years, most of that, 83%, is going to be back down to safe background levels, which means you can take those products, which actually were produced in the reactor. There's some very interesting things you can get out of that, and you can sell some high-quality materials. And the remainder only needs 300 years approximately for storage, which you can imagine finding in many places around the world that can handle that, and you can imagine making storage vessels that can last 300 years.
Weinberg called it burning the rocks. He said, boy, this is so good that you could literally mine rock just for its energy content. The average crust of the Earth, a cubic meter of average crust has about 12 grams of thorium in it. And that would be enough to power your life for about 10 to 15 years at Western standards. So that's an awful lot of energy.
We have 3,000 tons in storage owned by the United States government that were extracted and isolated during the Manhattan Project. And certainly at least 400,000 tons more of reserve in the United States today. So it's plentiful.
Going back to Eugene and Enrico, he asked a really logical question. How are you going to prevent losses? Because protactinium is going to gobble up your neutron. Wigner, I really think, was one of those minds that was accidentally transplanted from the future. I mean, he was just so far ahead of everybody else. And he said, we're going to build a fluid-fueled reactor. That's how. As a chemical engineer, he was used to dealing with everything in fluid form. When you use chemicals or you use reactants and so forth, if you got a solid, first thing you do is you turn it into a liquid. When you're done, you can turn it back into a solid. But you do everything as a liquid. We were going to have this liquid core that had the uranium-233 in it, and it was going to be fissioning, and it was going to be throwing these neutrons out, and it was going to be turning thorium into uranium-233. And then you were going to just chemically isolate this, and then they were going to put it back in the core. And so you just kept doing this process, and that was how you were going to make it work. In fluid form, you can get past a lot of the drawbacks of using thorium. Using solid form, you run into those problems with U-232 and so much. But there's another one, that's xenon-135. Xenon-135 is the biggest neutron poison we know of. It just loves to eat neutrons. It's like looking at Jupiter next to Pluto or something like that. I mean, it is just huge. And it gobbles up neutrons. This was a real problem when they built the first few reactors. Wigner realized in liquid form that xenon, being a gas, would just come right out. That's a very big deal. Reactor operators, they'd be happy to tell you all the troubles they have battling xenon in solid-fueled reactors. It's a real pain in the tail. So off they went in different directions. Fermi's group building the first liquid metal fast breeder reactors. Wigner's group building an aqueous homogeneous reactor, uranium in water. It had a lot of advantages, but it had one basic disadvantage. There was no aqueous form of thorium. You couldn't dissolve thorium into water. You could dissolve uranium into water, but you couldn't do it with thorium. They didn't know how to solve it. Well, they had this program to build an aircraft reactor, and most of them thought it was pretty hokey. They didn't think it was a good idea. In fact, Alvin Weinberg, who ran the lab, said it wasn't like we all of a sudden believed that nuclear airplanes were a good idea. It was the only way we could keep building reactors. A high-temperature reactor could be useful for other purposes, even if it never propelled an airplane. The scientists using the government's money said, okay, sure, we'll build you an aircraft reactor. Boy, it was super hard. You can only imagine if you're flying a nuclear bomber over Siberia and you run the reactor too hard and the engineer comes back and says, Captain, we're going to have to shut down for 9 hours because the xenon's overriding our reactivity control. I'll just put down right here on the snowfields of Siberia and wait for my xenon to decay away. They learned really quick. They're like, man, we have got to have a reactor that does not have this problem. How are we going to do this? Because we know this water version isn't going to work. What could we possibly make this out of? Hey, what about a fluoride? Fluorides are salt. Salts are really, really chemically stable. Because they're so darn happy being what they are, they can go to really high temperatures. And they don't have to have high pressures. This was the birth of the liquid fluoride reactors, to say, can we dissolve uranium and thorium into salts? Well, it turns out, yeah, you can. It's really easy, in fact. So they built this guy, the aircraft reactor experiment. This was the first liquid fluoride reactor. This thing ran for about 100 hours at some of the highest temperatures ever achieved by a nuclear reactor. And what's even cooler about it was it did it at atmospheric pressure. This wasn't some big high-pressure reactor. This was running at essentially ambient pressure. And they found out it was self-controlling. As the salt would expand, there was less fuel in the core, and so the reaction rate would slow down. And as the salt got cooler and got denser, there was more fuel in the core, and the reaction rate would increase. This reactor just basically ran itself. As they would increase the heat removal, it would power up. As they would decrease the heat removal, it would power down. You didn't have to use control rods or move it around. It was self-controlling. And it was chemically stable. You could have fission, and it would still not screw up the fuel. And fluoride fuel is the only way to build a high-temperature, high-power density reactor. If you build it out of solid fuel, you're going to be fighting your xenon. It was really easy to separate thorium and uranium. If you pop uranium in solution with fluorine gas, it will turn into uranium hexafluoride, which is gaseous, and that will just come right out of solution. So it was a one-step process to remove the fuel that you're making from what it is that will become the fuel, in this case, the thorium. This trick doesn't work in uranium-plutonium, but it does work in thorium-uranium because of the particular chemical characteristics of that fuel. The ability to separate this stuff is a big deal, and you can do it at high temperatures. You can do it in high radiation fields. It's an inherently chemical process. There's no cooling off that's required. I love this quote. Until then, I had never quite appreciated the full significance of the breeder. But now I became obsessed with the idea that humanity's whole future depended on the breeder. Now, when he says breeder, he means the ability to burn up thorium. And we tend to think of liquid metal breeders, but that's really what he's talking about. I understand that kind of passion because I feel the same way myself. This discovery of thorium and its potential, indeed, if we are going to have sustainable industrial society on this planet, it's going to be dependent on this technology. One day they were meeting in 1959 and they found out the Atomic Energy Commission wanted to build experiments. They had to cost less than $1 million. The guy who ran the molten salt reactor experiment, he wrote the proposal in a day. How many of you guys could write a proposal for a nuclear reactor in a day? So this is what the molten salt reactor experiment looked like. It was a bunch of graphite fuel elements in that tank, and then they would flow the fluoride fuel through it. And there's the salt pump and the heat exchanger. So you'd run the salt through the core, and it would get hot, and then it would give up its heat to the heat exchanger, and then it would all be driven by these pumps. And they ran this reactor for about 5 years, from 1965 to 1969. And during that time, they demonstrated a lot of the features that we would want ultimately in Lifter. Online refueling, they did it. This is actually a capsule, and they would load it up with new fuel, and they just drop it in the reactor. The fuel was in the capsule would just dissolve away. When they wanted to take out the uranium, they used fluorination. They could remove all the uranium. They took out some of the fuel, and they distilled away all the good stuff out of the fuel, and they just left behind the waste. And they had this fantastic safety feature. It's called a freeze plug. Because the fuel's so hot, if you cool it down, it will freeze and it will lock up in the pipe. And so they had a little blower over a flattened section of pipe, and it kept part of the salt just frozen right there in the pipe. If you lost all power to the reactor, if you turned all the lights off, all the juice off, that freeze plug would melt and the salt would drain out into a drain tank that was passively cooled. In most reactors, you have to take the coolant to the reactor in an emergency situation. And that makes them hard to build because you've got to have the regular core be able to run and make power 99.9% of the time. But then in an emergency case, you've got to be able to get the emergency coolant in and override everything else you've designed for all the other times. This reactor was completely opposite. You could have the core just do what it was supposed to, and then if there was an emergency, it would send the fuel to the place where it was going to be passively cooled. These guys, on Friday afternoon, they wouldn't want to leave the reactor running over the weekend, so they'd just go and they'd turn off all the power, and the salt plug would freeze, the thing would drain into the tanks, it would freeze up over the weekend, they'd come back on Monday, they'd turn the heaters on, they'd pump it out of the tanks back up into the core. So, I mean, they did this over and over and over again. The working example is worth stacks of documents in theory. How do you know this works? Well, they did it. It really worked. They demonstrated most of the features that are pertinent to this reactor. Well, after doing that, they really wanted to investigate how to build the real thing, and they began to go through different design concepts. This was about where they stopped on this design. They didn't know how graphite was going to respond under irradiation. But the really appealing thing about this approach was they had this super simple fuel cycle. You would make the fuel, you would fluorinate it out, you would introduce it into the core, you'd burn it up. When it was time to reprocess the core, you'd take out the fuel, you'd distill off the good stuff, and you were just left with fission products. A super simple, closed nuclear fuel cycle. Now, the real problem they had was with graphite. First, it would contract, and then it would swell under irradiation. And as they began to realize this, they thought a lot of our plans for how we were going to build this reactor aren't going to work just because of tolerancing and how graphite's going to change. The two-fluid reactor had a plumbing problem. So for us, the plumbing problem's got to be understood and managed. And I think it can be. I have some really good ideas of that. But the overall appeal of the two-fluid reactor is still great. And it really comes from that very, very simple fuel cycle. All right, so what happened to this? The Atomic Energy Commission was being run by a guy named Milt Shaw, and he was very driven to build liquid metal fast breeder reactor. These are Weinberg's words. He said, "Woe be unto any that stood in his way." Milt was like a bull. He enjoyed congressional confidence, so his position in the AEC was unassailable. It was clear he had little confidence in me or in ORNL. After all, we were pushing molten salt and not the fast breeder. More than that, we were being quite troublesome over the question of reactor safety.
Admiral Rickover and his program, a gigantic organization to build not only the Nautilus, but the whole nuclear Navy. He's done a very good job at establishing safety record. The Navy is excellent in that. Inherently, it's not found in the reactor. It's found in the very strict rules, the very well-trained sailors that run these reactors.
Alvin Weinberg invented the light water reactor. He holds the patent on that design that is so prevalent in the world today. He knew its capabilities and its limitations. He felt like this was a better approach. There was a congressman who ran the Joint Commission on Atomic Energy, Chet Holofield. And they were having a conversation, he and Milt and Alvin. Congressman Holofield got exasperated and said, "Alvin, if you are so concerned about the safety of reactors, I think it may be time for you to leave nuclear energy." Alvin Weinberg got fired. His opinions were at variance with those of the Atomic Energy Commission and congressional leadership. He'd called nuclear energy a Faustian bargain, and he promoted the molten salt breeders. When Weinberg got fired from Oak Ridge, their political protector was gone. It was not long thereafter the Atomic Energy Commission commissioned a report called WASH 1222, a review of the technology, very negative, completely ignored the safety, completely ignored the waste, completely ignored the proliferation. By the time the report was issued, 2 of the 3 issues they focused on had already been solved by the Oak Ridge researchers. The program was canceled in 1974. A bunch of Oak Ridge guys did try to kind of keep the torch burning probably into the 80s, but I've met with some of the old timers. There's really almost nobody there now who was involved in this. The vast majority of them are dead. I don't think there is necessarily a central nexus anymore for this. Personally, I'd love to see the United States do it. I think this would be a fantastic project for our nation, but there's no reason why any reasonable sized country couldn't go and make this happen quite successfully within their national resources.
It's a low fuel price, low capital costs, long life, low maintenance. You've got homogeneous mixing, which means you don't have any hot spots, which is a real concern in conventional reactors. One spot gets hotter and it continues to get hotter until you have a meltdown. You get to burn up all the fuel because it's constantly being moved around in the reactor, and no fuel shutdowns because you can fuel this continuously. The expandability of the fluid gives you a large negative temperature coefficient, which is where your safety is at. No separate cooling system. There is no coolant to get rid of in order to have a meltdown or a problem. The difference in size of a Brayton system versus steam plant. the cost of this whole system would be significantly less than existing nuclear power plants.
The basic physical advantage you have at thorium is you're starting at mass number 232, and you've got to march pretty far up the chain before you get to plutonium up at 239. As you march up that chain, there's two big on-ramps called fission, where you're probably going to get turned into energy. So you can run a thorium reactor in a way where you will make very, very little plutonium. In fact, if you pull out the neptunium, you'll make no plutonium at all. On the other hand, in a light water reactor that uses U-238, you're going to make plutonium on your very first step. You're going to absorb a neutron, and you're going to make plutonium-239. And it's not as good of a fissile fuel. If you want to avoid making the long-lived stuff, your best bet is to start with thorium. We've got spent nuclear fuel accumulating from our nuclear reactors. A typical 1 gigawatt reactor will make about 35 tons of spent nuclear fuel each year. They take this fuel, which is very hot because of the decay of the fission products, and they put it in these cooling pools. We're accumulating this stuff. This is the amount of spent nuclear fuel we have. It's not going to be long before our rate of generation of spent nuclear fuel is going to have yucca pretty full. If we start building more light water reactors, then we're going to hit those limits a lot sooner.
How do we start one of these machines up? Any kind of fissile material can get the process started off, U-235 or plutonium, or even leftover spent nuclear fuel from today's existing light water reactors.
Our current approach to nuclear reprocessing is based on dissolving nuclear fuel in nitric acid and liquids and so forth. You have to let the nuclear fuel cool down before you do it, and it's a very complicated, expensive process. The first thing you're doing is you're taking a solid and you're turning it into a liquid. And then once you turn it into a liquid, you're trying to separate all the piece parts and the components out. And then at the end, you're trying to take this liquid and turn it back into a solid again. Now, the French have really mastered this. I mean, they have a facility at La Hague where they do this, but it's a big facility, and they spend a lot of money to make this work. We know it's possible, but it's difficult. Now, on the other hand, the reprocessing the fluoride reactor is really simple. We just fluorinate the blanket, and we introduce it into the core. So this is a complete nuclear fuel cycle, boiled down to just a handful of steps.
This should scale up as well as scale down onto the back of a semi-trailer. If you really want to use other processes, when it's mobile, it can go to a site for shale oil extraction. Couples very well with desalination for water processes, hydrogen production as well, because of the high temperature nature of the reactor core.
What's the biggest obstacle? Is it funding? Is it political? One of the basic problems is this stuff is completely different than what they do in the nuclear world today. A few weeks ago, I was at the American Nuclear Society conference, and I mean, this is like the nexus of all of your best and brightest engineers in the field. Nobody knows about this stuff, and I don't mean that in a disparaging way. These are very, very smart people. I've almost finished my master's degree in nuclear engineering. In that time, I had one course that talked about breeding, and during that course, about 10 minutes of it talked about thorium, and during that 10 minutes, none of it mentioned fluoride reactors. So it's entirely possible to go to nuclear engineering school and get a PhD and have never been exposed to any of this stuff. Then when you do go get in the field and you learn how to run real reactors and solid core, and you learn how to control rods and feed water and all this other kind of stuff, it's like the difference between a typewriter and a word processor. You'll get the same thing in the end, but what's under the hood is just utterly and completely different. So I think the real nuclear industry looks at this and they go, well, what are we going to do with it? We'd be starting from scratch. It's great for an entrepreneur. It's rough for the legacy folks who would want to get into this.
Nuclear energy industry today makes all their money making fuel elements. It's very expensive. It's very exacting. Little zirconium cans with precisely measured oxides inside. This would make all the fuel kind of at the plant. That revenue stream would go away. And none of the incumbent players are really interested in designing a reactor that cuts off their big revenue stream in the future.
A lot of times back in the 60s, reactor vendors would sell reactors at a slight loss in order to lock in a long-term fuel fabrication contract, the razor blades approach. The whole cost structure around today's nuclear is really not amenable to this cheap, simple, easy-to-process fuel. We know that to tackle our global warming concerns, we're going to have to go after, number one, coal, and number two, transportation. Between this and electric cars, we could make a big difference. Also, ammonia is the basis of fertilizer, and fertilizer is the basis of modern agriculture. Right now, our fertilizers are made predominantly from hydrogen from natural gas. We need to be able to make ammonia for fertilizer in a non-carbon emitting way. We can take the electricity from LFTR to synthesize ammonia from atmospheric nitrogen and from hydrogen that we'd split from water. You can imagine LFTRs running kind of flat out all day long to make power for everybody, and then at night, when everybody turns off their lights and go to sleep, they switch over to make fuel for people or charge your electric cars.
This should be possible with uranium-238 and plutonium-239. You could breed uranium and then chemically separate those two species, but no one ever talks about that.
You can breed uranium-238 to plutonium-239, and you can do a chemical separation of those two. That's exactly what they want to do in fast breeder reactors. First of all, they're using solid fuel, So they have to irradiate the uranium-238 blanket for a certain period of time before it's economically advantageous to take it out and actually separate out the bred plutonium and then go and make new driver fuel to go in the core. So your first disadvantage is you're using solid fuel. That can be overcome. You can imagine fluid-fueled versions of the uranium-plutonium approach. But then that beautiful chemical trick I showed you where you could fluorinate the uranium out and leave the thorium, that doesn't work in uranium-plutonium. They're too similar to each other. In fact, if you go to try to fluorinate out plutonium from uranium, what will happen first is all the uranium will come out. If you're fluorinating a blanket of uranium, you're going to end up fluorinating all of it versus the stuff you want. The other part of it is the neutronics. You can't burn up the plutonium effectively unless you go to the fast spectrum. It's not impossible or inconceivable, but from an engineering approach, it's just basically a whole lot more difficult than doing it this way. As an engineer, I can look at this and go, there are really tangible, easy to do, already been demonstrated steps based on well understood chemistry that's been around 100 years that we can go and do it and make this happen. This isn't that hard. In conclusion, this gives us options for inherently safe, proliferation-resistant, economic nuclear power that can last thousands, if not millions of years. This really could be the silver bullet that enables us to power our industrial society. And this also offers real options for solving the long-term issues surrounding our existing spent nuclear fuel and ultimately preventing the formation of new transuranic waste. And finally, I want to thank Google. I love Gmail, and I love your search engine, and almost all the stuff I've done on this has